In this video, we're going to give an embarrassingly brief introduction to a very important numerical method when it comes to solving Maxwell's equations, which is the so-called FDTD method. Now, the FDTD method is an FD method, a finite difference method, of course. So we've been looking a lot at finite difference methods in the previous videos, more specifically when we were trying to solve the Helmholtz equation. But the Helmholtz equation is in the frequency domain. This guy here is a TD method, is one in the time domain method. So this means that we take Maxwell's equations and we also take them in all their full vectorial glory, so no more scalar approximations. And then we discretize the derivatives both in space and in time using finite differences. So that's the essence of the finite difference time domain method. There are some nice peculiarities about this method, specifically related to the fact that they're fully vectorial. And that is that you don't really calculate all the field components at all the locations in space. So if you look over here, you're calculating hx, for example, and then over there you're calculating ey. So why are they arranged in such a strange way? Why are the E fields and the H fields sort of like staggered? Well, the reason is that if you arrange them in this particular way, then you can sort of naturally express the curl equations of Maxwell, because here you see a magnetic field which is perpendicular to some sort of loop in the electric field. So that's a natural way that you can use to express then Maxwell's curl equations. This sort of staggering of fields at different components, of different field components at different locations, is also mirrored in the time domain, where there's also some sort of staggering going on, some sort of leapfrogging, where at one point in time you calculate the electric field, but then at the next iteration you calculate a magnetic field, and then you keep on iterating between E and H. You don't calculate both of them at the same time. So these are two nice features or characteristic features of the FDTD method. And again, you can go in a lot more detail, you can show lots of equations, but let's not do this in this introductory video. What is important to realize, of course, is that this is a very generic method. It can basically be used to solve anything, but it's also an extremely brute force method. It's not very clever, it's not very efficient, but if you throw enough resources at the problem in terms of memory and in terms of computational speed, then you can, in essence, solve anything. But you do need to be very careful when you look at numbers that come out of the FDTD method, or basically any numerical method for that matter, because you have these errors, intrinsic errors coming from moving to a discretized grid. You have to really look at the values that come out of the method. Do they make any sense? And it's very interesting to do a convergence analysis where you solve a certain problem for a certain grid size, and then you redo the same thing for a smaller grid size. And then you see, okay, if the results I get are very different in the two situations, then that means that my grid size was not fine enough. So always take what you get out of a numerical method, and especially FDTD, with a grain of salt.